here. And we are also being live streamed. So let me share. And how am I doing there with my share? Everybody see my slide?
Yes, we can see that.
Okay, great. Well, I want to welcome everyone to the 2022 winter meeting of the CESM Paleoclimate Working Group. My name's Esther Brady. I'm a project scientist at NCAR working in the Paleoclimate group. I'm co-chair along with Arnie Winguth, who's at the University of Texas in Arlington.
Hello, everybody. Great to see you.
Yeah, so first we're just going to go through some logistics. I'd like to direct your attention to the right figure, which is our code of conduct we've all agreed to observe. In our engagement, we'll offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, consider new ideas, and show appreciation. And I'd like to start by showing my appreciation for all the participants, the speakers, for your contributions to our dialogue and our discussions. Your participation is greatly valued and will help us share the course of the working group going forward into the future. And then now for some business. Speakers, please reserve the last 5 minutes of your time slot for questions and discussion. Listeners, please mute your mic when not speaking and use the raise hand feature that you can find in that lower reactions menu in Zoom. Please use the chat, which also you can find if you click on in the lower menu for any side discussions or comments, questions you might have, and the moderators will monitor that and read questions to the speakers. We're recording and we're live on YouTube right now, and we'll save the chat for later as well. Let me go to the next slide. So I want to first thank Tripti for a great seminar launching us off this week. It was a really great opportunity to showcase what Paleoclimate Working Group members do and how important our research is, especially for relevance to future climate. So looking ahead at the week, today we have 4 more talks, all really linked to the hydroclimate theme, and then a discussion at the end. Wednesday, we get started a bit earlier at 9:45 with like a virtual coffee for people to just check in. So look at the agenda for the actual time of the first talks if you're just listening. We'll have 7 talks and a discussion also at the end. And then Thursday, we have 7 additional talks and discussion. And then at 2 p.m., we have the first in our newly organized Paleoclimate Advances webinar series. And I know you've received some information about that, but we'll talk more about that as the week goes on. How are we doing time-wise? We are just about to get started. I'm looking forward to hearing everyone's research this week. And why don't we get started with our first speaker, who is Min Fu, graduate student at Harvard. And Min, I know you were here. I will stop my share. And
should I go ahead and share?
Yes, why don't you start your share? And are we on time here? Yes.
Great. I guess I'll just go ahead then.
Yeah, and one more thing for speakers, I forgot to mention that Arnie will give you a little warning at the 2 minutes to go point.
Okay.
If so, okay, great, thanks.
Oh, hi everyone. So the topic of my talk today is on the Pliocene climate, in particular, the relationship between warm sea surface temperatures near mid-latitude upwelling sites and their possible interaction with the hydrological cycle over land. So this is work I did in collaboration with Mark Kane at Columbia, Peter Molnar at Colorado, and my advisor, Ellie Zipperman. So as we often see in the news, recent years have seen intense drought over the Western US. As of July of 2021, 89% of the Western US was experiencing a drought. On the right is a figure showing North American drought conditions as of November last year. And as you can see in the dark red, much of the Western US is experiencing exceptional drought. Furthermore, the Colorado River, which provides water to over 40 million people, in 2021 reached its lowest level since 1937. So whether these recent precipitation deficits can be directly attributed to climate change is currently less than clear given the large role of internal variability. But regardless of whether these droughts were climate change related or not, climate models do predict a transition to drier conditions by the end of this century. So what are the mechanisms by which the Western US is expected to become drier? So the Southwestern US lies over the subtropics, which is where the Hadley cell descends. And in these subsidence regions, water is being exported from the atmospheric column. As the atmosphere holds more moisture in a warmer climate, these subtropical regions will export water more efficiently and become drier. So this is often called the dry get drier, wet get wetter mechanism. Furthermore, as the storm tracks shift poleward with warming, rainfall related to winter storms is also expected to decrease. So here's an animation from NASA showing changes in soil moisture in an ensemble of climate models under a business as usual scenario. And as you can see in the dark brown, large decreases in soil moisture are seen by the end of the century. Okay, so based on this, how does this prediction of drying compare to conditions in past warm climates? So Earth has experienced warm periods in the past, and we should verify this prediction by comparing it to those periods. So for this purpose, we'll introduce the Pliocene. The Pliocene occurred 5.3 to 2.6 million years ago and is often considered a useful analog for future warm climates. That's because during the Pliocene, the continents were virtually in the same position as they are today, with only minor differences. And the Pliocene occurred before the major Pleistocene ice ages that began around 2.6 million years ago. CO2 was probably between 350 and 500 ppm, and surface temperatures were about 3 degrees Celsius warmer than present day. So although it's considered a useful analog, it's important to note that it probably better reflects equilibrium climate rather than transient climate sensitivity. So now that we established the Pliocene as a suitable analog for future warm climates, what's the geological evidence for droughts over the Western US? Was it extremely dry? The answer turns out to be no. The Pliocene was actually characterized by dramatically wetter conditions over most subtropical land regions. For instance, over the Western US, sedimentary evidence indicates that there were large permanent lakes in the Death Valley region of Eastern California. One thing that I find quite remarkable is that Pliocene Lake Idaho, which is a lake that doesn't exist today, was comparable in size to some of the Great Lakes of Michigan. Furthermore, there's vegetation in the form of fossilized leaves and pollen that also indicates wetter conditions south of the Oregon-California border. So it's clear that considerably more rainfall was needed to sustain these lakes, which is in sharp contrast to predictions of future drying. So now I'll summarize a few key points, which is that, first of all, models generally don't reproduce a wet Pliocene Western US, which is shown by geological evidence. And previous suggestions include a weaker Hadley cell, possibly driven by a weaker meridional temperature gradient. Another idea is that perhaps it was sustained by a permanent El Nino or a warm Eastern Equatorial Pacific SSTs. And here we'll introduce a third possibility, which is that perhaps a warm California current, so a local SST pattern, sustained these wetter conditions. So this is a plausible hypothesis because warm SSTs along the coast may change the column water vapor, atmospheric circulation, and other relevant processes. But before I discuss this hypothesis in more detail, let me briefly mention coastal upwelling and Pliocene proxy reconstructions in these regions. So in the modern climate, equatorward winds along the eastern boundaries of the Atlantic and Pacific Ocean basins leads to 4 major coastal upwelling systems. And in these mid-latitude upwelling zones, they're characterized by strips of cold SST because of a combination of the advection of cold subarctic waters, as well as offshore Ekman transport, which leads to cold upwelling from below. And if we look at the SST signal during the Pliocene in these regions, if we look at the blue, green, and orange curves, which reflect SSTs along the California margin, SSTs along the California coast seem to have been at least 6 degrees Celsius warmer than present day. And this difference also appears at various other eastern boundary current regions, such as the Benguela Current, which is shown in the black curve on the right, where sea surface temperatures may have been as much as 10 degrees Celsius higher than present day. So this suggests that these boundary current regions must have operated quite differently during the Pliocene. And some previous suggestions for how these SSTs were sustained include perhaps a deeper ocean thermocline, or another possibility is that the upwelling winds in these regions were weaker. Now, if we consider how well the data, climate models do in these regions, on the right, we show a point-based data model intercomparison between Pliocene SSTs and ensemble of climate models, the Pliocene Model Intercomparison Project. So we see general agreement in many regions. However, if we really zoom in on the California current, we see that SSTs can be quite dramatically underestimated by 6 to 8 degrees Celsius. So this leads us to our hypothesis, which is that perhaps it's the fact that the model simulations are not reproducing a warm California current, which is also responsible for their failure to simulate wetter conditions over the Western US. So for this purpose, we'll use the CESM1 global climate model. CAM5 is used as the atmospheric component with about 1 degree horizontal resolution. And we'll use HAD-SST for our modern simulation. And we'll use the PRISM3 SST reconstruction for our Pliocene simulation. One thing that's important to note is that the gridded PRISM SST product actually doesn't reflect SSTs that are as warm as the point measurements suggest along these coastal upwelling regions. So the PRISM SST difference from modern shown in the lower panel on the right, it does reflect a large scale polar amplified warming, but it's not sufficiently warm along these coastal regions. So we'll also explore the effects of a warm California current by modifying this SST pattern. So starting with the PRISM SST shown in the colored contours on the right, we take the SST at the 150 degree west meridian, and we basically flatten the SST going towards the east. And this results in a SST difference anomaly that we show in the lower panel on the right. So we call this the PRISM 150 West simulation. And in total, compared to modern, this results in approximately 6 degree Celsius warming near shore, compared to only about 2 degrees in the original PRISM 3 data. So arguably, this is more consistent with the proxy evidence in these regions. So next, let's take a look at the annual mean rainfall signal. So on the left is the unmodified PRISM minus modern. And we see that much of the California coast actually becomes drier in this simulation. And there's a northwest and kind of southwest dipole with drier conditions over the Pacific Northwest. So the large scale PRISM SST differences alone are not sufficient to create wetter conditions in this region. However, if we consider PRISM 150 West with the warm California current, we see that it leads to greater rainfall throughout the Southwest and about 40% more rainfall in the Southwest compared to both the modern and PRISM simulations. So because extensive evidence of wet Pliocene conditions exists over the region shown in the black box, which we'll call the Southwest region, we'll average our data over this box and show the seasonality and mechanisms for greater rainfall over this region. So here on the left, we show precipitation, evaporation, and P-E for the 3 experiments. So in the dashed black curve, that's reanalysis. In the gray curve is our modern simulation. In the blue curve is the PRISM simulation. And in the green curve, it's PRISM with a warm California current. So what stands out on, of course, is that there's considerably more summer rainfall, especially during the late boreal summer during JAS. However, due to the aridity in this region, the increased rainfall is also balanced by much increased evaporation. So P-E increases in the summer. But if we also look at the winter season, even though the increase in precipitation isn't as dramatic, P-E is also higher in the winter. So P-E is higher both in the summer and in the winter, even though the increases in P are largest in the summer. So given the somewhat different behavior in winter and summer, next we'll investigate the atmospheric moisture budget for these 2 seasons separately. So now we'll introduce the atmospheric moisture budget, which states that averaged over time, precipitation minus evaporation in a column is balanced by the total water convergence. And using Reynolds averaging, we can further decompose this into its mean and eddy components. So the mean convergence meaning moisture brought in by the steady circulation, and eddy convergence related to transient eddies. And let's proceed to look at the hydrological cycle in the summer and the winter separately. So now we look at the JJA. On the left is the change in summer P-E as a result of the prescribed warming along the California coast. And then we also decompose this signal into its mean and eddy components. So as we can see, there's a very large degree of compensation between the mean and the eddy terms. But the fact that there are very large positive values in the mean convergence suggests that the mean convergence is the dominant factor in sustaining higher levels of summer P-E. So the explanation for this is that the increase in mean moisture convergence during the summer is a response to higher surface moist static energy. So moist static energy is a measure for the buoyancy of air parcels, and higher MSC reflects lower atmospheric stability and more favorable conditions for low level convergence. So the idea is that the higher SSTs lead to more low level moisture and surface MSC in the Southwest, which favors the development of convergent monsoonal circulation. And this is reminiscent of the North American monsoon, although strictly speaking, it's a bit north of the region that's typically studied when it comes to the North American monsoon. So next, we consider the DJF signal. So in contrast to the story with the summer, the DJF is mainly driven by changes to the eddy convergence. In terms of the mean convergence, there's increase over the Pacific Northwest, but there's a negative signal over parts of the Southwest. So it seems that in the winter, eddy convergence is dominant, plays a dominant role in bringing increased moisture. So the importance of eddies suggests that we should also take a look at the mid-latitude storm track. So we performed Lagrangian tracking of mid-latitude cyclones using the TRACK program developed by Hodges, which tracks cyclones based on their surface pressure anomalies. So on the left is the winter cyclone track density and particle trajectories in the PRISM simulation. And on the right is the difference between PRISM and modern. So indeed, there's a poleward shift in the storm track. And this is why, if we look very carefully here, that the PRISM simulation with the large-scale warming alone actually gets less winter rainfall than the modern simulation. So this is very reminiscent of the drying that we see in climate change scenarios. Yet, when we introduce a warm California current in the green curve, we see that rainfall in the winter now increases above both the modern and the PRISM simulation. So our interpretation for this is not complicated. On the left, we plot the anomaly storm track density and surface winds corresponding to days with precipitation in the Southwest US exceeding the 95th percentile. So this is the atmospheric circulation and storm track associated with rainy days in the Southwest. We see that indeed most winter rainfall is associated with storms over the Pacific Northwest, and these storms also advect moisture onshore from the region where SSTs are warmer and have a higher column water vapor by the Clausius-Clapeyron relationship. So even though the storm track density may be lower in this simulation, if the California current becomes considerably warmer, this higher specific humidity may allow fewer yet more intense winter storms to bring more rainfall to the Southwest in the winter as well. Okay, so a brief recap. It seems that warm California current leads to about 40% higher rainfall over the Southwestern US. This may be sufficient to explain Pliocene lakes and ecosystems. Rainfall in the summer is related to monsoonal circulation, and winter rainfall may be related to eddy moisture convergence from winter storms. So this hypothesis may be testable because if it's a permanent El Nino that brings this rainfall, that would be mostly winter rainfall. Yet if it's a warm California current, this may be associated with more summer rainfall. So this may lead to an isotope signal, and Tripti is currently working on this. So next, I'd like to just very quickly revisit the coastal upwelling. So we discussed these warm coastal SSTs, but how are these warm temperatures sustained? In the modern climate, cold SSTs are caused by a combination of coastal upwelling and equatorward advection, but and previous mechanisms include a deeper thermocline or weaker upwelling winds. But here I'll introduce a third possibility, which is could actually be the weather conditions which lead to the weaker coastal upwelling. So now we perform some idealized simulations where we add some fractional wetlands near the boundaries of all four eastern boundary currents. And if we look carefully at the surface fluxes in these simulations, on top we have our modern simulation, and we show the Bowen ratio, which is the ratio of sensible to latent surface heat fluxes, which is a common measure of land aridity. And it could be as high as 10 over deserts and very low on the order of 0.1 over ocean. When we force our simulations with the PRISM 3 SSTs as well as PRISM vegetation types alone, this isn't sufficient to make this region dramatically wetter. Yet if you add some wetlands by changing the land types in the GCM, you can basically make the Bowen ratio closer to 1, which is comparable to conditions over present-day eastern Colorado.
2 minutes.
So when the wetlands are added, the atmosphere receives less sensible heat flux. Surface temperatures cool in this region, which leads to an increase in sea level pressure. This weakens the land-sea pressure gradient and also leads to weakening of alongshore wind stress. So similar differences can be found at 3 out of 4 of the major eastern boundary currents. Basically, only at the Humboldt currents in South America, we don't see any significant changes from this modification. This may have to do with the fact that the Andes topography strongly constrains the atmospheric circulation in this region. And as we can see on the right, at 3 out of 4 of these upwelling sites, if you kind of impose wet conditions, this can lead to decreases in both coastal and offshore upwelling indices. On the left is a plot of the change in cumulative upwelling flux integrated only over days that meet a threshold for 3 continuous days of strong upwelling winds. And we can see that for the Canary and California currents, this modification can lead to up to 50% decreases in cumulative upwelling flux. So 50% reduction in the upwelling winds has been shown in high resolution ocean simulations to perhaps lead to 3 to 4 degrees Celsius warming. So recap, by prescribing wetter conditions onshore, this weakens land sea pressure gradients and may weaken upwelling favorable winds. Warm coastal SSTs lead to greater rainfall over the adjacent subtropical continents. So we identified a possible feedback that might transition the Western US to wetter conditions in a warm climate. So thank you.
Thank you, Min Min, for a great talk. Very interesting. I see a lot of hands being raised here, so that's really great. Let's see. Who? Usually they pop up in order that they were raised. I don't. Oh, that was clapping. Sorry.
I guess those were clappings.
Lots of clapping. Okay. Any hands raised for questions? Paul?
Hi. So, are you suggesting that these the wettening of Southwest United States is almost like a tipping point where we could see a wettening in the future if we somehow made the region more wetter? Somehow?
Yeah, this is something I've been thinking about, but for now I can only speculate on what might kind of trigger this feedback. Perhaps when the deeper levels of the ocean warm up, this could be kind of a tipping point that transitions the climate to a wetter state. But I think this is an open question and I'm not quite sure. I would love to discuss it more, yeah.
Thanks.
Oh, is there a question from Tripti?
Oh, Tripti, yes, sorry.
Yeah, that was a great talk, Min Min. I was wondering if you could get a similar feedback if you just prescribed lakes instead of wetlands. You know, you'd still change the Bowen ratio potentially.
I think so. I think that would probably achieve a similar effect. I'm not sure if there's evidence of lakes being that extensive during the Pliocene. It probably might not be physical to apply very high percentages, but I think functionally speaking, it would probably achieve a similar effect.
Jean Zhu, would you like to ask your question?
Hi, Mimi, great talk.
Oh,
I have a question about the second part of the talk. So did you prescribe the wetlands all year round? If you do this seasonally, will that make a difference?
Yes, so they're prescribed all year round. There is an upwelling season in the modern climate, and yeah, that depends on every site. So the upwelling is definitely strongest over certain seasons. I'm not sure what would be the effect of prescribing it seasonally right now, but yeah, if they exist during the upwelling season, then it would have a greater effect, I imagine.
Thank you.
Jessica Tierney?
Yeah, hey, that was a great talk. Thanks for sharing. So my question is more of a geological one, which is that how do you think these conditions were initially established in the Cenozoic, and when? You know, if we're basically we think about, is the transition to sort of the modern California current regime, do you think that was due to ice sheet growth or CO2 or both?
Great question. I think if you look at like SST proxies, they just get warmer as you go prior to the Pliocene, right? So I imagine that I think it was also wet in warm climates prior to the Pliocene in this region, if I'm not mistaken. So it could be possible that the onset of glaciation cools the North Atlantic deep waters, and then this leads to kind of colder SSTs at all upwelling sites, and then this is what leads to a transition to dry regions. to a dry regime, at least during interglacial periods, because the Western US, for instance, was also wet during ice ages. So yeah, I think it's possible that the onset of glaciation plays a role in setting up these conditions.
Okay, I think we're going to need to move on to our next speaker. Ren, if you can ask your question in the chat, or maybe save it for when we have some discussion at the end of the day, that would be great. And now we have our next speaker, who is Mary Grace Albright from the University of Connecticut, my graduate student. And Mary Grace, would you like to share your screen?
1 second.
Oh, there you are.
Oh no, sorry. Apparently, I've never shared my screen on Zoom before.
Oh,
Okay. Okay. Can
here
you
we
all
go.
see?
Very
Perfect.
good.
All right. Let's see. Okay. So I'm Mary Grace, and I'm a first-year graduate student from UConn working with Rhiannon Tripty on an NSF-funded project to understand changes in the North American monsoon during the mid-Pliocene. So first, I know this has already been covered a couple times today, and this figure looks a little familiar, but I wanted to start by giving some background information on the mid-Pliocene and point out a few important features that are here. So we're studying the mid-Pliocene to see how the North American monsoon could potentially change in the future. And so not only did this time period have similar topography and bathymetry to our current Earth, but it was also the last time that it saw an atmospheric CO2 level that was similar to present day, so around 400 ppm. And our estimates of warming during this time, which you can see in the chart right here, we're about 1.8 to 3.6 degrees warmer than pre-industrial, which is right here. So here in this chart, we use pre-industrial as our base period. So similar to that, pre-industrial is listed at a change of 0 degree temperature, and then mid-Pliocene goes from about 1.8 here to about 3.6. And these temperatures are similar to predicted warming in the future based on intermediate warming scenarios, which is highlighted here in this blue area. And now the usefulness of this time period as an analog for the future is further supported by a number of existing climate simulations, which put the mid-Pliocene as the closest representation of future climatic conditions by 2040. So this figure on the right here shows the percentage of land with climate change predictions following RCP 4.5 that are analogous to the Pliocene, the Eocene, the last interglacial, the Holocene, recent historical data, and pre-industrial. So you can see by about 2040 here, the Pliocene becomes the most prevalent analog. And they use a combination of mean summer and winter temperatures along with precipitation to assess this similarity. Now, in terms of the North American monsoon, it is an atmospheric circulation feature of hydroclimate in the North American Southwest, and it's generated by interactions between topography and moisture surge from the Gulf of California and the Gulf of Mexico. So it starts to develop in Mexico around June, then moves into the US Southwest in July until about mid-September. And during the development of this monsoon, the strongest precipitation is generally located on the western side of the Mexican mountain range, which in this figure would be about like right here. And this graphic here is just an example of summer circulation and precipitation patterns illustrated by the water vapor satellite imagery. So the dark blue, green, and red areas are areas with thunderstorms, where the orange areas are areas with drier air. And so this is an example from August 22nd, 2018. And you can see the development of strong moist convection in the rain band in Mexico on the western side of where the mountain range would be. And this monsoon is an important feature of hydroclimate in Southwest North America, with many areas really depending on its rainfall. So for example, Mexico receives over 75% of their annual average precipitation during this monsoon season, with Arizona and New Mexico also receiving more than about 50%. And this means that future changes would have a really large impact on the people living in this region, which makes it all that more important for us to understand how it might change. Now, this monsoon was traditionally thought to be thermally forced, where the land and mountains heat up quickly during the summer, creating low pressure and moisture convergence towards the land in high topography. However, more recently, a new study demonstrated that the mechanical forcing by the Sierra Madre Occidental mountain range in Mexico is perhaps more important than thermal forcing. So here in these three figures below, they are the summer, June, August, and September precipitation, and then the contours are the near surface eastward wind. And on the right here, this is a simulation that they ran with modern orography present. And in this simulation, there is a clear band of summer precipitation in the monsoon region. And yeah, so these contours would be the near surface eastward wind. And in this middle figure where they ran the simulation with flattened orography, there's essentially no rain band here in the middle in our monsoon region, and the eastward wind stays to the north and south of our region. So this means that with the mountains, there's moisture convergence to the western side of the mountain range, which leads to locally enhanced precipitation forming. And with these simulations, high horizontal resolution is really important for capturing a lot of the key features of this monsoon. So right here are two of the same models that were run at different resolutions. So on the left is 2 degree in land and atmosphere, and on the right is 0.5 degree in the land and atmosphere. And the red box is our main monsoon region that we're concerned about. And on the left, in the lower resolution, you can see that the ring band of monsoonal precipitation is quite poorly defined, whereas on the right, you can only really start to see the clear monsoon ring dependency on topography in the high resolution simulations. And within these simulations, as mentioned before, the North American monsoon is predicted to weaken in response to future warming. So here in this top panel, we can see the percentage July precipitation change that was induced by patterns of SST anomalies. So here, once again, is our monsoon region, and all the areas in red are areas where the precipitation is expected to decrease. So that is essentially all of our monsoon region right here. And in the bottom panel, we can see that along with these changes in precipitation, there is relatively cooler SST relative to global mean in the subtropical Northeast Pacific, paired with relative warmer sea surface temperatures in the Eastern Tropical Pacific. And so these patterns mean that there is moisture divergence along the Southwest North American coast and convergence towards the tropics, which would take moisture away from our monsoon region. Right now, moving past background information, just to put this in a general context, for my PhD thesis, I'm hoping to explore how we can use high resolution simulations to help bridge the gap between model results and proxy data. And in addition to this, I'm looking to explore how weather systems change during the warm mid-Pliocene climate state and what the implication of these results are to predicted future hydroclimate changes. And so this presentation shows the first steps that I've taken towards this. And so here, the two main things that we're addressing are, we're looking at a comparison between the high resolution and low resolution simulations of the pre-industrial North American monsoon. And then additionally, we're looking at a comparison and the simulated changes of the mid-Pliocene North American monsoon in relation to pre-industrial. Now, the model that we used for the high resolution simulations was the CESM 1.3. The spectral element dynamical core was used for the atmospheric component, where for sea ice, community ice code version 4 was used. For ocean, parallel ocean program version 2 was used. And for the land, it was community land model version 4. And now the resolution for these simulations in the atmosphere and land, it was run on a cube sphere with 6 faces and 120 by 120 elements per face. So this is equivalent to about 25-kilometer lat long resolution. And then in the ocean and sea ice, the typical 1-degree resolution was used. So both model components and resolution for the ocean and sea ice are actually identical to existing mid-Pliocene simulations using CESM 1.2. And now for the setup of these simulations, the boundary conditions come from PRISM 4D, which are outlined by Dowsett et al. In 2016. And this maps to the high resolution topography and bathymetry, but no information from the past. We didn't have any information from the past to map the subgrid scale topography. So we used modern subgrid scale remapped with nearest neighbor. And the initial conditions for ocean ice, land, and terrestrial carbon cycle come from a 1,200-year-long simulation from a previous mid-Pliocene run. And then the only part that was initialized from code was the atmosphere. And this initialization allowed for a fairly short spin-up time where it equilibrated within the first 5 years. So to the right here, we can see the global average of the top of atmosphere radiation imbalance as a function of model years. So compared to the last 30 years of the pre-industrial simulation, the last 25 years of the mid-Pliocene simulation with the same model configurations has pretty similar top of atmosphere radiation balance. They're both pretty close to 0. So because of this, we're taking the last 30 years of simulation to compare the pre-industrial to the mid-Pliocene runs. Excuse me. So in this presentation, I'm mainly going to look at the added benefit of high resolution to the mean climate state. So this is just a first look at this data. We're currently working on a more detailed analysis for the future. But first, I want to talk about the difference in elevation between the low resolution data on the left and the high resolution data on the right. And in the high resolution, you can see that there is better resolved elevation and geometry of the Sierra Madre Occidental Mountain Range. So on the right, the mountain range is very confined to the west of Mexico, and it sits at a higher elevation in the high resolution than it does to the low resolution. So in the low resolution, there's a more diffusive mountain belt, which covers a wider area. Now looking at precipitation in this region. So here is low resolution summer and winter precipitation. And then on the right, here is high resolution summer and precipitation, or summer and winter precipitation. And in the summer, in the high resolution, the band of our core monsoon precipitation is narrowly defined to the western side of the Sierra Madre Occidental Mountain Range, whereas in the low resolution, the band is more diffusive and it runs across the mountains. And then based on these plots here for the winter, there's not much difference in the precipitation from low resolution to high resolution. Now, following this, we have mapped the airflow patterns at a level of 700 millibar. So in the red, we have contours of the mountain range, in both the high resolution on the top and low resolution on the bottom. And the key thing to point out here is that in the high resolution, there is a greater deflection of northward flow compared to the low resolution, which you can see by these arrows here. And when you have this northward deflection, you're going to expect a compression of the air column and enhanced stability. So this in turn limits the amount of precipitation that we might expect to see developing here, which helps to explain the difference in precipitation that we saw on the last slide, where the high-res precipitation was much more confined by the better resolved topography. So now moving on to the comparison between the Pliocene and pre-industrial data that we have. So first, I did want to acknowledge that there are actually differences in elevation between the Pliocene and pre-industrial in our simulations. So here is Pliocene high resolution, and here's pre-industrial high resolution. We did not include the low resolution because the difference between them is the same for both the high and low resolutions. But here is a difference plot with Pliocene minus pre-industrial, and you can see that there is actually lower elevation in the Pliocene. And this difference is based on the geodynamic model that was outlined by Dowsett et al. In 2016, which runs to adjust topography on Earth due to the loss of Greenland and West Antarctic ice sheets. So this is a figure from their paper. We've outlined here our area of interest, and the blue indicates all the regions with lowered elevation in the Pliocene, or in the mid-Pliocene. And you can see that essentially all of the Mexican mountain range is lower. And so in terms of what this means for annual precipitation differences, we can see consistent bands of drying in both of these resolutions here. We can see that, we can see that lowered elevation in the Pliocene leads to an anticyclonic circulation, which you can see in these arrows here, at 850 millibar forming in front of the mountains in both resolutions. And so this takes precipitation away from the region, resulting in drying to the western side of the mountain. And this is due to the lowered mechanical forcing that I mentioned in the beginning, as reported as by Booz et al. In 2021. However, when we look at early summer precipitation changes, there's actually more of an enhancement in the eastern monsoon rainbelt during early summer in the high resolution run. And these findings are consistent with proxy evidence from Tripty's group of wetter rather than drier conditions during the mid-Pliocene in this region. So with this, here you can see the airflow, or you can see in the airflow patterns, the moisture convergence from the wetter nearby ocean in the high resolution, which compensates in the Pliocene for the reduced orographic lifting at higher elevations. So that could help to explain why there's this wetter band to the east. Now, we've only started exploring what might be the reason for this wetter band during the Pliocene. And one hypothesis that we've come up with is the difference in sea surface temperature response between the low and high resolutions. So here we can see that the top one is high res and the low one, or the bottom one, is the low resolution. So in the high resolution, we can see that there is greater warming in the North Pacific, extending all the way to the western coast of Southwest North America. And so this means that there would be greater evaporation and hence moisture transport towards Southwest North America. So you can see here that there is a warming blob or marine heat wave that is occurring in the high resolution simulations that is not present in the low resolution.
2 minutes.
And so this anomalous coastal warming by the Southwest North American coast helps explain changes in the wind patterns. So just to conclude, we have 3 main points that we outlined through this presentation. So we saw that there were substantial differences in monsoon state and the pre-industrial simulations, which can be attributed to better resolved topography. And then we saw that there was a better defined precipitation band with reduced precipitation east of the Sierra Madre Occidental Mountains. And we think that the high resolution simulations are likely generating more realistic projections of hydroclimate here. And then we also saw that the mid-Pliocene annual precipitation was controlled by the elevation of the mountain range. And we also saw that enhanced mid-Pliocene early summer precipitation in the high resolution run, or we saw that there was enhanced precipitation in the high resolution run above the Sierra Madre Occidentals. And we think this might be due to the simulated SST warming blob off the West Coast. And lastly, our results suggest evolving SST patterns and interactions with hydroclimate over this region with continued warming, which is better captured in the high resolution simulations. So since this was just a first look at our data, we have a number of future directions that we're planning on exploring, such as the decomposition of precipitation between large scale and mesoscale systems. Also, we're planning on looking at the influence of circulation patterns on the formation and trajectories of mesoscale systems, and then looking at water isotopes in the high resolution simulations once these become available. And then lastly, the version of, there's another version of the high resolution code with 10-kilometer resolution ocean and sea ice that has not been explored for paleoclimate. So our simulation was run at a 10-degree resolution ocean and sea ice, but we think that a higher resolution here could be really important for our results. And that is what I have. I just wanted to acknowledge the funding sources for this project, but yes.
Thank you, Mary Grace. That was a great talk. I'll open it up to questions. We have that's a clap, okay. I'm learning the difference between clap and question. Yeah, we have a few minutes for questions before we, Min, I'll recognize you.
Oh, hi. Should I go ahead?
Yes.
Just curious, is there any benefit to using the spectral core instead of the finite volume? Is there any benefit or drawback to that?
That is a good question. So these simulations were actually run before I joined the program. So I was not part of the first simulation runs. So I actually am not positive.
I don't know if
Thanks. Yeah, that's fine.
Ren wants to pipe in on that, or
Yeah, I can chime in on that. So the reason for using the spectral element is that it scales better with adding cores. So for those simulations, we run with more than 10,000 cores. So if you use finite volume, at some point, adding more cores is not going to help you run faster, but spectral element does have that benefit of scaling really better by adding cores. Yeah.
Thanks.
okay. Any further questions? Paul.
Hi, great talk. So I guess I had a question with your, for the simulations, it seemed like you ran them for 25 years, but they're fully coupled. Or did you run a fixed SSC runs first that were like 25 years? Is that correct?
Wait, sorry, can you repeat the last thing that you said?
So you ran your simulations for, it says like 25 years, but it seemed like they were fully coupled simulations because it seems like your SSTs are able to evolve. Is that correct?
So we have 35 years fully coupled, and then we just averaged the last 30 years of the runs that we had.
Mhm.
Does that answer your
Okay.
question?
Yeah, I mean, it seems like it seems like you should run the model a lot longer if it's a fully coupled simulation, but it seems like your TOA is in balance, so it's probably good. I don't know if Rand want to chime in.
And were these branched off of the lower resolution runs?
Yeah, so those are branched off from the CESM 1.2, so the equilibrated ocean state. But you do see SSC pattern, which to us it formed pretty quickly. So perhaps it's more of a upper ocean response, perhaps to cloud formation changes, things like that. That's our hypothesis.
Yeah, because it seems like if we run a high resolution and then you can get that induced warming without doing any other sensitivities, then it's maybe it's a resolution in terms of the Pliocene, the Plioclimate models not capturing that SST patterns.
Okay. Oh, go ahead, Ren.
Yeah, I would comment. It also perhaps has to do with model sensitivity as well. We have CESM2 simulations, which also seems to have a much stronger coastal warming than those simulations we have.
So, I mean, this is something that would be great to talk about in the discussion too, because there's some real limitations with using high resolution models, and we can kind of talk a bit more about that sort of thing later on. But we should move on to our next talk, if you don't mind, and that is Arnie Winguth from the University of Texas at Arlington. So take it away, Arnie. I'll be timing a couple minutes behind, but.
Can you see the screen now?
Yes.
Okay, thank you, Esther, for giving me the opportunity here to speak at the Paleo Working Group meeting. So this paper or this talk, I want to focus on kind of redoing or revisiting the paper of Carmichael 2014 EOMIP paper, which addressed the hydrological cycle at the PETM. And so we have now newer simulation with CESM 1.2. And so we can compare our simulation with the historical simulation done with CESM 3 and a Hadley model. I acknowledge my co-author, Katrina Wazowski and Jay Wang helped me also plotting. Graduate students helped me plotting some of the graphs, also Michaela Brown, and of course I acknowledge Jen, Jeff and Christine and Matt, who helped set up the model run for the Eocene. I also acknowledge the sponsors which made these long-term run possible. The Paleocene Eocene summer maximum, you saw that on the previous talks at the very left. I don't want to show the graph here again, but it's quite an interesting event about 56 million years before present. It's an abrupt global warming equivalent to about 4 degrees warming globally. First detected in a Nature paper or referred for in a Nature paper of Kenneth Stott in 1991. It's also associated with a pulse of CO2, and it has been discussed as a suitable analog for anthropogenic climate change. Also, there has been quite a debate in the community whether the rate of climate change at the PTM was even slower what we are expecting today. And I think this applies to multiple time slices in the past. So we may need to go even deeper in the time to find equivalent rates. Maybe the Permian-Triassic would be one. It's also quite fascinating of the ecosystem and evolutionary changes. The onset of the evolution of mammals, transition of monkeys throughout the continents. The hothouse climate has been also The PTM has been also of interest because dwarfing of animals, which has been seen also in other times of hothouse climates. And so horses, which are quite large today, were cat-sized during the PTM. I showed the first figure, which showed some fossil leaves, and you saw a lot of holes in it. And so it's also a time of increased insect population and a large turnover of global carbon cycle and associated with a warming, ocean acidification, also partial extinction of foraminifera, which I gave a talk in previous Paleo Working Group meetings. So the main objective is here how changes in the hydrological cycle contributed to the stresses on the ecosystem. We are focusing here on the hydrological cycles, not on the impact. And so we used here the deep map version of CSM 1.2 Paleo version, which has improved radiative transfer scheme. This is still a CAM4 simulation, so a more conservative approach. And we are following here the initial condition of deep map in our study. The model has been physically spun up for 2,000 years and reported about the carbon cycle, but there's much more to come in the future of the carbon cycle, since we are almost now have 2,000 years in for the BEC also, including a marine ecosystem. And Jia Wing is doing her PhD thesis on the carbon cycle changes. So in terms of the hydrological cycle, CSM2 is less advanced than CSM 1.2 is less advanced than CSM2, but still has some improvement compared to CSM3. And is, of course, much faster to run compared to CSM2. And so it has a better improved convection scheme compared to CSM3. So if you compare the results with CSM3. And but there are still biases. We see first the double ITCZ, which is common with many climate models. And we see also that the Eastern Equatorial Pacific is too wet compared to NCEP simulations. The surface temperature at the PTM here shown at the top, the difference between 6 times CO2. That CO2 value as part of the deep map protocol is thought to better fit the CO2 concentration of the PTM, whereas the 3 times CO2 simulation shows a more suitable fit to the late Paleocene. And so we are interested in this transition from the late Paleocene to the peak PTM. And so the warming is reproduced with these differences from 3 times to 6 times CO2, but not in the high latitude. And for that, one likely would need to have a higher CO2 level. But the challenge of a higher CO2 level is that the interior of the continents become too warm. Also, the paleo CO2 reconstruction would not really support that. Shown here, the 6 times CO2 simulation, as I've shown in previous talks, provide a reasonable fit for most parts of the world, but there's still a bias in the high latitudes, so poles are still too cool. What's notable, if you are talking about the insect population, so we are warming from 3 to 6 times CO2 the planet, and this gives also more favorable condition to insect population. I've read that insect population have actually the favorite condition at 30 degrees to 32 degrees. If it's too hot, they're coming also under heat stress, and if it's too cold, they don't have a high population. The climate sensitivity here in relation, I know Sean has also done a newer simulation with CAM5 and CSM2, which have a higher sensitivity, but here shown comparison to the Carmichael paper. And so the trend of CSM2 is the same kind of than previous, particular that, so there's 3 CSM circulation carried out. And I mostly focus on the comparison between CSM 1.2 and CSM3. There has been 3 CSM3 simulation, one by Matt Huber with more transparent clouds, so lower cloud optical depths, lower cloud forcing. Then the simulation I carried out, which used more the present day aerosol forcing, and then one from Jeff Keel and Christine Shields. And that had a higher sensitivity where they used a cloud optical depths and cloud properties kind of comparable to the oceanic conditions. So the idea was we don't have so much continental aerosols due to anthropogenic perturbation if we're looking in the present day aerosol distribution. And so it should be more likely than oceanic. And this has a higher sensitivity, even than our CSM1 simulation I'm presenting here. Okay, so the hydrological cycles of precipitation increasing with the CO2 radiative forcing. And here we have the warmer temperature simulated with CSM2, which is on the one hand, there's the cloud forcing, which plays a role, but we had also a less reflective land surface, which led also to warmer temperature. But the trend, the slope is quite similar to the previous simulation. Here is only the outlier from Keel and Shield, which is more similar to CAM5 in terms or the CSM2 and the sensitivity. What is of interest is also the comparison here between the different CSM3 simulation, the percent increase in the hydrological cycle in precipitation here per degrees Celsius. And so we are in the ballpark here. So here we have the global temperature versus global mean precipitation in millimeter per year. And here the similar for CSM, this study. And so we see here the kind of slope here, the 1 times, 3 times, 6 times, and 12 times CO2 simulation, which we have carried out. So this is actually quite consistent. What is of interest is also that the convective events, convective precipitation actually follow also this trends and the total precipitation. So here are shown now the maps of 1 times CO2, 3 times, 6 times, and 12 times. This is annual mean precipitation. And so from 1 to 3 times, you see a boost in the hydrological cycle. What we heard in the first talk, so the wet get wetter, the dry becomes drier because a more effective moisture transport towards the intertropical conversion zone. And we see this expansion then further of lower precipitation in the subtropics and higher precipitation, particularly along the intertropical conversion zone. And so India is located directly at the intertropical conversion zone, and we see actually a massive precipitation over India in this simulation. So it has been discussed that in CSM3, the total the precipitation over land and ocean are quite similar. And the values here is the ocean has still a little bit higher precipitation here compared to the land here shown both in black, the 6 times CO2, and red dashed as a 3 times CO2 simulation. Below also the difference is shown. So you noticed there's only one exception where the land, or 2 exceptions where the land is actually higher, and then that is this extreme precipitation, which you saw on the previous slide here. So this is located over India, and the other over Africa, Northern Africa, and northern South America. And the second peak here in precipitation that is linked over Patagonia and Australia, and so that's why you have there locally some higher precipitation compared to the ocean. So the patterns in precipitation follows kind of the historical EUMIP simulation. The units are here slightly different, and also from north to south, whether this is here from south to north. So one needs to virtually flip the graph. So the magnitude of the CSM circulation follows here kind of the extremes which were presented in the Carmichael paper. So it's you saw this extreme intertropical convergence zone is slightly higher than in the previous simulation. The model is also higher resolution. The previous simulation had 3 degrees, and also the topography is better resolved, so that also favors an higher precipitation. Here shown are the differences in the precipitation. Above is the 6 times minus the 3 times CO2, which is kind of what we're seeing as an amplification from the late Paleocene to the PETM. If we support our fit with the temperature data, and we see here again the intensification of the IDDC, and also the high latitudes get wetter and the subtropics getting drier. We see similar patterns here in the Hadley model and the CESM3, but the CESM3 with PreIndustrial with current aerosol forcing had a lower sensitivity. And then, of course, the most extreme scenario here, just with comparable magnitude of PCO2 change, is showing here much higher sensitivity of CSM 1.2 compared to CSM 3. So P minus E is of interest. So that shows us better where we have more aridity and where is the humidity. And here are the changes of P minus E, 6 times CO2 minus the 3 times CO2. So we see that the subtropical region, in particular here over North Africa, the thesis becomes drier, but also over South Africa. There we are reaching an extreme temperatures also of 60 degrees Celsius and more. So this is inconsistent with the increased aridity. And then the amplification over the IDCZ, as I pointed out, and wetter high latitudes, as has been supported also by fossil data and isotope work. So the P minus E pattern here in a slightly different range, as has been proposed by Carmichael in his paper, showing here that the CSM 1.2 simulation best fit the most extreme of the CSM3, and then probably the simulation of Christine and Jeff are the better simulation here, or the most extreme simulation fits here the CSM 1.2. Yeah.
2 minutes.
Okay, yeah. The changes in the seasonality here, typically one I have 4 seasons, but here I have only the 3 month seasons. Identify here also that during the summertime, we're seeing actually more intensification of the hydrological cycle over the summers, as said with the North American so-called monsoon. The topography is slightly different. We see also strong changes in the hydrological cycle, as well with monsoonal circulation over Asia, and Africa, and the tip of South America. And this is then reversed during winter time. So there we have more in the southern hemisphere or monsoon circulation. Comparison then with the data reveal reasonable agreement between the CSM estimates and that from fossil plants and pollen data, as summarized in the Carmichael paper. What's interesting is the hydrological cycle for Patagonia totally underestimated. This is likely because we don't resolve the Andes mountain ranges. There's also temperature, local temperature may be an effect. And also Antarctica, we underestimate the precipitation. It could be also that the data are seasonal bias, and that could lead to some differences between the models. So more exploration needs to be done. So in summary, the simulation with CSM 1.2 confirmed previous EUMEP study that the hydrological cycle is amplified towards the PTM. We expect that also based on any future climate change scenarios. A difference in the warmer temperature changes drive the higher precipitation compared to previous EUMEP simulation, particularly compared to CSM 3. So we have these hotter temperature and thus higher precipitation. And the simulations also, this simulation simulates also warmer polar temperature, and that represent better the higher high latitude precipitation compared to previous simulation, and trends the magnitude of simulated precipitation patterns generally agree with the constructed rainfall estimates, but biases remain in the high latitudes. And that's all. Thank you.
Thank you, Arnie, for a great talk. And I'll open it up to questions. See clapping. It's interesting how there's a contrast with wet get wetter, dry get drier in a kind of a global view. But if you look regionally, you don't necessarily find that, like we've seen in the Pliocene North American monsoon region. So that's kind of interesting. I think they've seen that before, looking into the future, future scenarios as well.
We have one talk, Min Fu.
Oh, Min Fu,
yeah.
Yes.
Oh, I just wanted to ask, have you considered using your output to compute weathering rates? If you have P-C, that should you should have runoff from these simulations, right? That could be interesting. You could estimate how long PECM lasts.
Yeah, I haven't had time to look into the runoff rates. Yeah, that's actually interesting. The runoff rates actually caused a lot of challenges in the beginning. So we had actually so massive runoff that the ocean model crashed, and we had also in the original simulation we had a mass imbalance. So we fixed that eventually. Yongsu fix that, and but yeah, this is massive. The runoff, particularly in the tropics, is massive, and so would expect extreme weathering rates. Yeah. I looked actually also on the upwelling. The upwelling, at least between 6 times and 3 times CO2, changes mostly in the equatorial region, but not along the American coast. So that's actually, I saw there's some interest to look actually also in similar regions, but we don't have the resolution. We have only 2 degrees resolution compared to your simulation.
Yeah. And your ocean was 1 degree resolution?
Ocean was 1 degree, correct, yes. Yeah, yeah, but the atmosphere, we run it at 2 degrees.
Yeah, the ocean 1 degree model doesn't do coastal upwelling very very well. There's notorious biases there. So
Yes, that is well documented.
okay, do I see any other questions for Arnie? If not, we can move to our last speaker of the day, Paul Acosta, who is at the University of Michigan, postdoc. And ready when you are, Paul.
All right. One correction, I actually moved universities.
Oh, okay. I just want
so
what was put in the spreadsheet. So
yeah, so I actually just recently moved to George Mason University this past January. So, but a lot of the work that I'll be presenting are work that I've done with Chris Polson at University of Michigan.
we don't see your slide. We see like your slide, all your slides. There we go.
There you go.
Yeah.
So yeah, hi everyone. Today I'm going to be talking about the evolution of the Atlantic intertropical convergence zone from the Cretaceous. And before I begin, I'd like to thank my collaborators, Chris Polson, Jung Zhu, and Jean-Baptiste Ledant, who essentially helped me set up some of these runs. And really, my talk is going to be focusing on the impact of widening the South Atlantic Basin, shown here, on the South American and African monsoon and rainforest system. So we all know that paleogeography in the past varied quite dramatically. So this is a video created by Chris Cotis and Nicky Wright, showing that the expansion or divergence of the South American and African continents from when it was essentially the West Gondwana supercontinent. And essentially giving, forming the South Atlantic Basin through time, which then has impacts on the atmospheric and oceanic circulation. So there's more recent studies that have suggested that paleogeography has a substantial impact on the monsoon circulation. So this is a study by Alex Farnsworth showing changes in paleogeography in Asia has a humongous impact on the South Asian monsoon as well as the East Asia monsoon. Where here is showing in the Sinditinian, you have this drying of the South Asia monsoon relatively to what a modern boundary condition showing a modern type South Asian monsoon system. And also more recently, there's a modern day studies showing the importance of the fetch or the width of the South Atlantic Basin. Here's a study by Liwi and Battisti demonstrating that the width of that basin impacts the moisture flux into South America, and essentially the greater the width, the increased moisture flux into South America, as well as the strengthening of the South American monsoon system. But more importantly, using these simulation, we can try to understand and try to piece together what the ecosystem looked like in the past. So here's just kind of a compilation of macrofossil assemblages from South America and Africa. Here in the late Cretaceous, you see increase in numbers of species abundance in pollen records. Then you have that massive decline during the 65 million year extinction, and then a rebound of species abundance in the Paleocene Eocene thermal maximum boundary in both South America and Africa. But more interestingly, you see in the Neogene, you have a decrease in macrofossil assemblages in Africa, but then you get this increase in number of species in South America. So there seems to be a disconnect between the two continents. And a lot of the Paleocene Eocene studies out there mostly talks about these megathermal rainforest systems, and there exists because of high CO2 conditions and strong precipitation rates in the tropics. So the study really aims to try to understand what the forest system could look like in the past. And we all know that CO2 has been changing over time. So this is just a global compilation of sea surface temperatures from Delta 18.0 forams. And here's showing the records from Cretaceous all the way to modern day, and essentially showing tropical SSTs versus highlighted SSTs in both in the Cretaceous as well as the Pliocene, Eocene thermal maximum. SSTs were much warmer than modern day as well as in the Neogene. So how are we going to tackle this problem? Well, we're going to be using the CSM version 1.2. And many of the simulations I'll be showing has a low CO2 condition. So you have pre-industrial condition CO2, as well as higher CO2 conditions for the middle Miocene. We're at 400 ppm CO2. In the early Eocene and the late Cretaceous, we're running 6 times pre-industrial CO2. As for the boundary conditions, for the middle Miocene, I'm using the Goldner et al. 2014. For the early Eocene, I've used Zhangzhu's runs. And for the late Cretaceous, I'm using Jean-Baptiste Ledon's Sudamanian simulations. So the plots on the right are showing paleogeography and paleotopography. So elevation in meters. And you can just looking at this, it looks like topography quite differ from one time period to another. And that's most likely due to the boundary conditions that was being used. But what I want you to really focus on is that the widening of the basin and as well as changes in paleotopography. So like in the pre-industrial, you have a high Andes versus the previous time periods. And then as well as the East African Rift Zone, which is very high in the Sudamanian and much different than what it is in the Eastern simulation and the Miocene simulation and the pre-industrial simulation. So, and also keep in mind that not only that the paleogeography or the basin is widening, both South America and Africa are also moving northward. Africa is moving towards Eurasia, while South America is moving towards North Africa, essentially closing the Panama Gateway over time. And to tackle the how to understand the rainforest system, we didn't run dynamic veg in our simulations, but we are able to use these climate classifications. So we're going to be using the Köppen-Geiger climate classification, where you set a limit of temperature and precipitation, and you can get a typical modern day tropical rainforest, as well as a tropical monsoon and tropical savanna. So here in PLL 2007 study shows in blue the extent of the tropical rainforest system in South America, as well as a tropical monsoon in lighter blue, and as well as the tropical rainforest system in Africa. All right, so on to some results. So these simulations only has the low CO2, and here you're just comparing it with ERA interim just to see how our model's doing. And the top panel is showing austral summer precipitation in millimeters per day. And the bottom panel is showing boreal summer precipitation. And the features we want to focus on here is, of course, the Atlantic intertropical convergence zone, the South American monsoon, East African monsoon, and the West African monsoon. I think some of you have known that a lot of the climate models have this double ITCZ problem. So we can see here comparison to the ERA interim, you have this double ITCZ. But I think in terms of capturing the monsoon systems, South American monsoon, you can capture that Eastern Amazon basin precipitation pretty well, as well as orographic precipitation over the Andes. Although the ERA interim is a 1 degree resolution simulation, and this is a 2 degree resolution. So if you run a 1 degree pre-industrial, I bet the simulation will probably look a lot better. In terms of the East African monsoon, the precipitation maxima is a lot further south. Here it's around 20 degrees south, while in the ERA interim, it's around near the equator. And for the West African monsoon, you see enhanced precipitation in the western coast of West Africa, but then much drier in the pre-industrial versus the ERA interim. And if we look at our paleoclimate simulation, so again, we're just showing austral summer precipitation. In the Sundomanian, you have this mega monsoon type circulation where most of the continents experience substantial amount of rain. And you see these precipitation centers are most likely due to the orography that we put into the simulations. But in general, you can see that enhanced precipitation over South America and Africa. And then in the early Eocene simulation, you begin to decouple that mega monsoon circulation. And you have essentially your South American monsoon is restricted toward the western side of South America, where your East African monsoon is not really changing too much. And further on, if you look at the middle Miocene simulation, you have this expansion of the South American monsoon towards the eastern coast of South America, as well as the formation of precipitation over the coast, which is not present in the early Eocene and the Sundomanian simulation. And we look at the boreal summer precipitation, looking at the West African monsoon. You have, since Africa is near the equator, essentially the tip of West Africa is near the equator, you have this dramatic increase in West African monsoon precipitation when you compared it to the pre-industrial. And this is the same case for our Eocene simulation. But then you start to see this like drying over the continents like our pre-industrial, and it could be a model bias in when we compare it to ERA interim. And then when we look at their middle Miocene simulation, you see this extension of the Atlantic intertropical convergence zone, like the pre-industrial, as well as the ERA interim. And that is essentially showing that the Atlantic intertropical convergence zone is in full swing during the middle Miocene, and it's much smaller in the early Eocene and the Sundomanian. Now we look at the impact of CO2. So this is just looking at austral summer precipitation between the low CO2 simulations versus the high CO2 simulations. And interestingly enough, you can see that most of the precipitation patterns are the same, but they're more enhanced essentially. And I think perhaps it is either a function of the low resolution nature of the model, where we can't change some of the SST patterns, as we talked about earlier. But essentially, if you're in the tropics, you have wetter region getting wetter, but then if you're in the subtropics, dry regions essentially stays dry in these simulations. If we look at the boreal summer monsoons, so you look at the West African monsoon, it's essentially the same pattern, right? You have enhanced precipitation where there's precipitation already occurring, but the subtropics still remain dry. So using our paleoclimate simulations, we can then use the precipitation and the temperature distribution to then use these Köppen-Geiger climate classification to then distinguish what the South American and African rainforest system looked like in the past. So here we're just showing what pre-industrial is, what modern day could look like. And then in the Sundomanian, the low CO2 simulation, you can see this expansive rainforest system in dark green, and as well as the Eocene in the Eocene. But if you notice, there's still some drier regions in the East South American continent, while that then expands during the Miocene due to mostly the enhanced coastal precipitation in the Miocene. And if we look at the higher CO2 simulation, you then get an expansion towards the poles of these rainforest systems. And you even have an expansion of the monsoonal rainforest system, both the Siberian and the Eocene. So it seems like CO2 in terms of using this classification has an impact on where the rainforest could thrive during those time periods. And in the Miocene, since we have a modest increase in CO2, the rainforest patterns don't really change too much. So that could essentially explain a lot of it. Could explain the paleogeography, can explain a lot of what the rainforest system distribution looked like as we move from a narrowed type paleogeography toward a wider paleogeography. And here I just wanted to compare back to what some of the previous studies have shown, these like mega thermal rainforest systems. And looking at South America and Africa, you can certainly get these type of mega thermal rainforest systems, but in terms of looking at regional patterns, this is not the case where you have an expansive Amazon rainforest in the Eocene or the Cenomanian, which doesn't occur because you essentially have a drier Eastern Amazon basin in these two simulations versus what happens in the Miocene. So in conclusion, the widening of the South Atlantic basin through time altered the regional atmospheric and oceanic simulations. And I didn't show any results from the oceans, but in our paper, which is in review right now, there's a ton of other analysis on this stuff. So definitely stay tuned. During the Cenomanian and the early Eocene, when the basin was much narrower, the ITCZ essentially was non-existent, where you have this mega monsoon circulation, right? And the South American monsoon was mostly restricted toward the northwestern corner of the continent. But then your African monsoon system, since it was located further towards the tropics, are much wetter than what they are today. But as the basin widened, the Atlantic intertropical convergence formed, and the South American monsoon expanded eastward, essentially also expanding that Amazon rainforest. But then since your paleogeography is changing and your Africa is moving towards the north, then the West African monsoon is then centered towards the subtropics, making it essentially drier in the Neogene. The impact of CO2, I would suggest, is secondary to paleogeography in terms of what the precipitation patterns look like. It does have an impact on somewhat the polar extent of the precipitation, since you have certainly somewhat warmer conditions that are allowing more precipitation in the tropics as well as some parts of the subtropics. And using the Köppen-Geiger climate classification, we suggested the Amazon forest was restricted toward the western corner of South America during the times when the basin was narrow, but then was able to expand as the Atlantic intertropical convergence zones form. And that in our Cretaceous and early Eocene simulation, we certainly have seen a pan-African rainforest existed, essentially a large rainforest system, much larger comparable to what it is today. But then that's partly controlled by CO2 and paleogeography, and that changes in the location of the West Africa, essentially going from the equator to the subtropics, essentially controls that strength of that West African monsoon. I'd like to take any questions.
Thank you, Paul. Open up for questions. That was a great talk. I see a question from Jeremy Rugenstein.
Hi, Paul. That was a really great talk. Thanks for sharing that. My question has to do with, and maybe I missed this in the boundary condition slide, but how do you vary the vegetation in the Amazon? As in, like, do you change during the Cretaceous, change from mostly gymnosperms to angiosperms between the Cretaceous and Eocene runs? And here I'm just wondering about all the work that Jung-Lin Lee and Kevin Boyce did, showing that this transition alone has a big effect on the hydrological cycle.
Yeah, so the vegetation in our simulations are they're essentially fixed, right? So you change them by changing a plant functional type, and you're right. So the vegetation in extinction 65 million years ago was like very different to what it is today, and there's more recent study that is showing that changing ancient plant functional types could actually have a huge impact on essentially the monsoon region and all the megathermal rainforest systems. So right now the model is only using plant functional types from the modern day, and I think adding those ancient plant functional types could really have a huge impact on the circulations that we're seeing. But yeah, if we could use a dynamic veg, that would be amazing. But sometimes it just doesn't work out. So,
well, thank you.
We hope it does work out in the future. Okay, Tripti, you have a question?
Yeah, thanks for a great talk. And this is sort of riffing off Jeremy's question, but there's modern literature that suggests that SST biases in the tropical Atlantic are strongly influenced by convection biases over the West Africa, as well as the Amazon. I wonder if you can shed light on some of, you didn't talk about it, but how ocean circulation interacts with convection changes on land.
Yeah, actually, I have a slide. This is just one example of that, right? So this is just SSTs for 3 paleoclimate simulations, where you have in the early Eocene, you have essentially a warm northern Atlantic basin, because essentially this basin is already wide. But since you have a somewhat limited circulation here, you have a somewhat cooler SSTs in the southern hemisphere versus what it looks like in the middle Miocene. And that SST pattern essentially allows that convection over the South Atlantic, Eastern South American basin to occur, and that in the Eocene that doesn't happen. So you have this suppression of convection over the region. So yeah, SST patterns has a huge implication on the regional circulation.
Cool, thank you.
Anyone, any other questions? There's a comment from Christine about the dynamic vegetation model FATES that is being developed for the terrestrial CTSM terrestrial system model. Yeah, sorry, which is a dynamic vegetation model, like a ecosystem type model. And we used to have a dynamic veg model in CCSM3 that we used in the past, and through CCSM4 and CESM 1 and 2, we haven't had that capability. So that's something to talk about in our next discussion period, about how we can lobby and support that functionality in the future for paleo. Do I see any other hands for questions for Paul specifically? Anything in the chat? No? So, Ren, you have a question.
Yeah, that was a great talk, Paul. And using this Copenhagen classification to really pinpoint to the comparison with proxy, I think that was a really great idea and great implementation. I have a question though, because those classifications, if I understand it correctly, are based on like present day threshold, right? So I was wondering, so do you encounter a situation that you cannot find an analog in those runs, let's say, especially for like Cretaceous?
Yeah, so I've actually had a conversation with a couple of folks about this, right? So especially in the Paleocene, thermal maximum where temperatures were a lot warmer. And it's kind of a pitfall of these classifications because they set a minimum temperature, essentially the coldest month of the year, right, for your plants to live. But then you don't know what the maximum temperatures are. And I think in terms of the proxy folks, they're working on that in terms of what conditions plants can live in terms of like the highest temperatures they can thrive in. But yeah, you're right. So like in terms of the tropics, the temperature in my simulations are very warm. So you could also just say this region, you can't classify it because they're not in the modern day bounds of temperature. But certainly in the precipitation patterns, I think those ones are okay to use, but then the temperatures when they get like 35 or higher, they're like, I don't know if we're able to use it. So yeah, you're right.
Okay. Yeah, thanks for the response. Yeah, it seems like perhaps paleobotanists can help actually narrow down perhaps making new envelopes, or maybe it's just models too warm, then we just can't really.
Okay, there is a question in the chat from Min Min Fu for Paul. Could the presence of the waterway in Western Africa also contribute to an enhanced paleo monsoon?
Yeah, certainly. I think in terms of changing the SST distribution, especially for the East African monsoon, right? So a lot of that moisture comes from that region. But I think a lot of the climate models have a problem simulating that region, which is, so the warming pattern we see there in the Miocene could be somewhat biased in terms of how warm it is. But yeah, actually, in terms of the East African monsoon, a lot of the changes in precipitation is mostly linked to topography. So even if we put a warm SST there, you could see a greater increase, but not as great as like increasing the height of the East African ridge zone. So yeah.
Okay. One more question from Arnie. I don't know if it is.
Yeah, I just want to make a comment to Rand's concern. I think the best thing is, I think that has been addressed, and also to Paul's comment. I think using the Köppen-Geiger classification has been used throughout the past. I remember that John Kutzbacher and Fred Ziegler used kind of these classification to reconstruct the Permian climate. And I think the best thing one can do for the past is using some suitable analog. So if you have the paleoplants, finding the suitable analog where these paleoplants live presently, and so infer then about what climate zone it would be. But so it has been, so the approach using the Köppen-Geiger classification has been used throughout the past and previous studies. Yeah.
Thanks, Arnie. Good to know.
Yeah.
Thanks, Arnie. Okay, I think we're ready to move on to our open discussion. And if it'd be great to have, yes, Betty has turned on her her camera, which is great. So, and I do have a slide I can kind of get us started off with. Let me share my screen. I don't need to keep it up. I think we'll just run through some questions that I had as I kind of thought about what the speakers had for us today, and my own thoughts, knowing what our activities are in the working group and how we have a new proposal that we'll be writing for more computer time, starting, we'll be writing it in the summer for the next 2 years. And I'd like to hear from the community your thoughts on some activities that we would put into the proposal, also modeling capabilities that you would like to see to advance your research and paleoclimate science in general. So let me share. Yeah, here. And I just put up some questions for discussion, and then I'll take it down, and so everyone can kind of see each other and not just the blank screen with words. So first, we can start with some comments that came out of the talks today, or questions, further questions. But also, I just had some thoughts. Maybe it looks like the research that we heard today, like Tripti's talk, has been combining information from the proxy record with new modeling approaches in order to advance our understanding of hydroclimate and what that implies for future climate change, and how can we maybe improve our approaches there, what new modeling capabilities would help advancing the research, and then for past to future, what simulations or time periods should be new or renewed focus. We don't have to really address any of these today. We have other discussion sessions for the next couple of days, and I just wanted to get us going here. So yeah, I'll just get us, I will unshare and open it up to general comments or questions.
I mean, oh, go ahead.
Go ahead. Oh.
Well, for the proxy model comparisons, isotopes are extremely useful,
Yes.
right?
Yeah, you demonstrated that.
Yeah.
And I was glad you did that during the CGD seminar, because the CESM2 is not fully implemented with isotopes, and we've had, it's been difficult to get them into all the components as they develop new versions. So having support for the community, from the community for those, is essential to putting the pressure to having them in our next versions of the model. So yeah. Betty, see you.
Yeah, I just want to comment. Thinking about Tripti's seminar is there's a lot of simulations out there and more being done, but we're not always aware of them. And what Tripti and Ren did is start with some simulations that Ren had, but then run atmosphere only with fixed SSTs. And so if there was a better way to advertise everything we're doing, people are running the Miocene, the Cretaceous, but not everybody knows. So we're hoping to do that on our Paleoclimate Working Group webpage, but we really need help so that we can build on things rather than redoing things, not knowing that somebody's already run the CESM 1.2 Cenomanian, for example. So that's my one comment. Because we learn a lot from those extra sensitivity simulations, as you showed, Tripti.
Yeah. Ren, you have your hand raised.
Yeah, I just want to echo what Betty said. It would be great to know what are the simulations out there, and perhaps some kind of community resource page that can host data simulation people contribute, and then future work can either use the data or connect with people who actually run those simulations.
Mhm.
And the other thing, since you mentioned about the resource,
Yeah.
I think for the Pliocene, the sensitivity experiments would be very interesting, and the high resolution simulations. So that's something, if there is resource, could be taken advantage by the community. I think that would be great. The other thing is, well, the high resolution simulations, I think it's really also could use isotopes. Currently, we don't have that.
Mhm. Yeah, I think the talks today really emphasized the need for high resolution modeling simulations and approaches. And it's something that's takes a lot of computer time. I mean, they generally are slower in terms of model simulations you can produce per wall clock day. You know, they're more expensive to run. They take more computer time. Yeah, I mean, I think we're just starting to get some experience in running high resolution coupled models, especially for paleoclimate, and also actually for pre-industrial and future climates. They're just so computer and people resource intensive that for climate problems, they're you know,
Right.
a big project to do. So Ren, you still have your hand up?
Yeah.
Yeah.
Yeah, I'll just lower it.
Oh, okay. Well, you have the experience, so please weigh in on the high resolution. Jessica?
Yeah, I dropped in the chat that I agree. It would also be great if we had a campaign, like, I mean, this is maybe asking for something we don't have space for, but if there was a way to like organize the paleo run somehow, somewhere in a storage area, you know, once people are done publishing their papers, it'd be great to have one place rather than, you know, having to email, you know, a bunch of people to find out where it is. So that's like a, I don't know, a Christmas wish sort of thing. But the other thing I was going to say is, so I'll talk about this on Thursday, but, you know, my group's been doing a lot of paleoclimate data assimilation with the paleoclimate runs, and we in order to do that, you need model simulations of time periods that are like slightly different from each other. So that could be like, you know, you do a simulation at different CO2, or maybe you change, I don't know, something in the model. You could change like a parameterization. And so one of the things we've had trouble with the data assimilation is having enough variety in the paleoclimate simulations so that the assimilation can actually run. And it's really hard because these runs are already so expensive, right? And so it's like you're somewhat limited. But if there's a way to brainstorm, how can we run like, kind of thinking about the last Millennium Ensemble, you know, how like that there was real value in having that big ensemble, and we probably can't run like all these ancient time periods like 1,000 times, but we could, you know, maybe having more variety, like trying to change things a little bit, you know, maybe, yeah, tweak some parameters or something, or change the paleotopography to try and sample that space would be really helpful for paleo DA, but also kind of just to understand the sensitivity to things like Rand's work has shown by, you know, testing topography and then vegetation and the Pliocene and things like that.
Yeah, we have, well, Clay Tabor did some idealized paleoclimate simulations that kind of spanned a parameter space. So like high CO2, low CO2, eccentricity, you know, high eccentricity, low, various orbital changes. And so we do have that set from CESM 1, I believe. So but those are kind of idealized simulations, all based on modern, you know, land ocean bathymetry, topography, vegetation data sets. So it might not be the variety that you're thinking of that you would need to do the data assimilation that you'd want to do. So, and the story, you probably know from your own experience how difficult it is to get large amounts of campaign storage, especially for external community members from NCAR, people working outside of the CESM project. We just don't currently have space, and it's not in our data management policy to host on that CESM campaign storage runs that others have done. It might be something to lobby NSF for, you know, but right now, yeah, it's a great wish list. And it's also would require, you know, data managers and things that we also, we do our own data management, and it's, we're a bit behind there, I would say, in terms of pulling things together in the spaces that we have in a sensible way. So yeah, it's good to note and add to our wish list. But yeah, Arnie?
Yeah, I think with the data, you probably don't need to sample all each month of a 2,000 year simulation or so. I mean, then you have a large data inventory. But if you do maybe seasonal or monthly means or 50 or 100 year averages, then your storage becomes relatively low. And one can easily probably use the paleo allocation to store these runs. I see you can't really store the complete runs. And this is also limited to the NSF project you have as a PI, and that expires afterward. But it may be suitable to, maybe we could agree on maybe just means, seasonal means, so monthly means of long-term averages, and maybe the annual means, then the amount is reduced. Yeah.
Yeah, like some climatologies and
yes, right. Yeah.
Yeah, and already we host various data sets, like observational data sets, in the Climate Data Gateway, and it might be something that Betty, that we can do. Betty might know more about what we can do with the Climate Data Gateway than I, but it's something that could be quite interesting. But again, it's a big management task, I would think. So yeah, Betty? You're muted, yeah.
No, that wasn't what I was going to say, but yeah, the Climate Data Gateway, or Jess asked about the ESGF, and the second I don't know, but the Climate Data Gateway still comes from our storage like campaign. So that's even if you can get it there, so it's easier for people to find, it's still part of that quota. Now I was going to ask, both Arnie made me think of something, and before that, Jess, I think one should consider now that we're way more concerned when we think of the future of extremes, that at least the last part of your run to really talk to people and think about even higher solutions. So, 6 hourly and 3 hourly, if you want to look at the mesoscale convective complexes that you have in Texas, Arnie. So, you don't need for like the host spin up a lot of things, but really at the end you should. But more to Jess's, this has been kind of my dream, Jess, except we get overwhelmed with PMIP and CMIP. So we do one simulation for, the last millennium now, or one for, there's an effort in the software engineering group to create containers, they call them, and they basically put everything you need. Let's say you want to rerun the Pliocene run. So you have the Pliocene CMIP, PMIP run, everything, the data sets that go in, all the software that goes in, so that a student then could actually more easily take that container and say, I want to run different CO2s, or I want to fiddle with this or that. So I think really that's going to be huge, but we're not big enough at NCAR to do it all. So if these containers made it easier for grad students then to run, and I'll look at it more because maybe it's something in the future, for example, Paleocamp might want to think about using for projects.
Mhm. Mhm. Clay?
Yeah. So I was just going to comment, going a little bit back to advertising things that are available, and also recommend that maybe there could be some type of advertisement for developments that have come out in the model. For example, there is an ICAM 6 now that's been published on, but if I hadn't just stumbled upon that paper, I don't know if I would have known that was even available. And I know like some other things, after having left NCAR, that you kind of fall out of the loop sometimes of what things might be of interest for, things like NSF proposals and collaborations. So I don't know if there's an easy way to do that on the Paleo working group page, but maybe just flagging a few developments, either in terms of papers or presentations that, could be expanded further and used for Paleo applications.
Yeah, you brought up something that we are wanting to do and have in the pipes to get our Paleo webpage kind of revamped, retooled, kind of get it more up to date. And one of those items is like recent and notable. It can be simulations or, like you said, a publication. We also have on there an item which is for the university to contact us, and we can advertise their simulations that are available, and put some links in there and some documentation for those simulations. So I'll talk more about that on Thursday. I have a talk that has a slide that kind of talks a little bit about our Paleo webpage and what we'd like to see there. But it's great to have to hear what you want to see there, because that will help us get it shaped up for you. So I've written it down and noted it. So anyone else? Tripty had to leave. She'll be back in the coming days. So let's see.
I was just
Play again.
another random
Okay.
idea that maybe
Brainstorm.
work or not. I know some of NCAR is trying to work with, I think, Amazon to use storage, and I'm not sure if that's something that we could easily do for most of our simulations because they might not care about it too much, but maybe for some of these high res extreme events, there might be enough interest that maybe they'd give us a bit of space. And I don't know how we would pursue something like that, or it's something we can pursue on our own, but just looking to outside people who might be interested in the data for one reason or another that would be willing to host it for free.
Yeah, I went to the tutorial on intake ESM, which I think is what you're referring to. And I did notice they were drawing data from Amazon Web Services for that tutorial. So it's something to look into. I'm not familiar with what they're doing there, but that's a good thing to look into. They had the large ensemble runs there that they were pulling down from that. So, and showing us how to use it. Yeah, that's a good point. We could look into that.
So my understanding, and I only have a little bit of understanding, is uploading data to the cloud is free, but downloading isn't. And so covering the cost of that, and sometimes like probably Amazon Cloud covers some of that, but I just had one more thought and maybe people could think about, and again, we need your help if we're going to do this, is I've become enamored with Python notebooks. I can't do them, but I watch other people do them. And, some way of sharing, whether it's setting up a boundary condition or an analysis program or whatever, some model data, and I think my internet's going unstable, so you may not hear me, would be great, so that, we can do that. I know Chris Brearley's group has done that quite a bit with PMIP, so we could start looking there at what they have established.
Yeah, we do have a link to our GitHub repository page from the Paleo webpage that Christine helped get set up. And yeah, okay, so we do have some community input there, but you're right. I think maybe we don't advertise it enough. Maybe it's an issue with everyone's time commitments because it takes time to contribute these things. But yeah, I think that's good. We can maybe start there and see how we can better formulate it for the community. It does take people contributing to it and sharing, but yeah. I think you can find the isotope enabled CESM on that GitHub page. So anyway, yeah, so. Christine's got her thumb up, yay. Do you want to add anything, Christine?
No, I just like the GitHub is the perfect place to put all of that stuff.
Yeah.
So I think
It's just a matter of,
yeah. Yeah, I know we set it up specifically for contributions. So I think that's, and then you can, like the GitHub is where people tend to share notebooks anyway. So that could be a really good.
yeah. But it's been my experience though, learning Python and Jupyter notebooks that at least from what is being done at NCAR, there's a number of different projects and there's like almost no one place to get all of the projects that are out there, even from that are being done at NCAR. You get various GitHub repositories and they're just kind of, I guess you can find them under the NCAR/NCAR, I think, but yeah, I think it's worth trying to maybe make it easier to find them all and link them in. Yeah. Yep. Okay. So
The link, Esther, I put up for Chris
Yeah.
Burley and Annie Zhou's GitHub, which is interesting. People might want to look at it.
yeah, so maybe one of the first things we can do is ask them if we can, I'm sure it's fine with them, but we can ask to put a link to their GitHub repository from our GitHub Paleo Resources page. So, and try and get it better advertised in the future.
I suggest something about
Yeah.
Python.
Uh-huh.
So as far as I checked recently, the GeoCat has not imported the Paleoland mask function. So that's kind of the thing for.
There's a lot that they haven't pivoted from NCL to yet. Pivot to Python was the phrase that we started with a couple of years ago. But yeah, there's definitely some examples there, but not everything is there. So so maybe that is, I think you can request things. I'll look into that, but if there's a need for that.
Seems like Christine might have an answer for that.
Christine, yeah.
I've been tortured by this whole pivot to Python thing too. So, and I've been trying to like import or change different scripts and stuff. And so no, the GeoCat is actually not the best way to move to Python. If you want to convert straight from NCL to like Python, GeoCat's really not a good way. There's like other libraries you can import. That's like one thing. And then the second thing is that if you do want to use things that they aren't in the, like this, for example, one of the kernels that they provide for on Jupyter Hub for that CESL does, then you can just create your own kernel and import your own stuff. So that's a workaround.
Yeah.
Right.
So for those may be feeling like out of the loop here, there's been a series of tutorials that on Python and the Python ecosystem for that have been hosted by some groups at NCAR, and an effort to move from NCL, the NCAR graphics library, to Python versions has been something ongoing for the last couple of years. And and that has kind of ended up in GeoCat and GeoComp and various things like this. So I do encourage you to look at the Project Pythia page, and you can kind of go from there to a lot of examples, and also I think the tutorials that are kind of helpful. So that's what I've been doing to try to learn the new way. So. And
I just put the link up to that page that Esther was talking about. So that has.
Oh yeah, ESDS. Yeah. It's kind of a multifaceted effort across NCAR. So, but there are about monthly tutorials, and they're also recorded to YouTube, and they're great to watch on YouTube. I do that. And you kind of miss the chat portion of the actual live tutorial, but it works well, I think. So
the blogs are really helpful because they have like frequently asked questions. So if you're wondering how to speed up your import of CSM data, go to the blog and you'll find an entry there for that.
Yeah. Yeah. So we are getting to the end of our discussion time. Anyone else have anything they want to bring up? Thank you all for coming. Thanks, speakers, for some great talks, and look forward to the days ahead for more great talks. And hope to see you there. And guess we'll adjourn. Oh, Clay, you have something?
No, that was supposed to be a wave goodbye.
Oh, that's a wave.
Yeah.
Okay.